Okay, so let's determine the properties of this graph. First thing I always suggest to do is to locate the axis line. So the maximum value here looks like the scale is going up by 0.5. So the max value is at 0.5, and down here this would be negative 2.5. There are formulas to find the axis line and the amplitude, however it's just counting, so it's using number sense. The distance from negative 2.5 to 0.5 is a total of 3 units. And if I take 3 units and I cut that in half, that's 1.5. So that tells me if I go 1.5 from the bottom or 1.5 from the top, I'm going to have the location of my axis line. That is also the same as averaging the distance from negative 2.5 to 0.5. So if I average 0.5 plus negative 2.5, take that and I divide it by 2, that gives me negative 1. So that's where my axis line is, by averaging the max and the min value. So the axis is at negative 1, so that's the equation of my axis, y equals negative 1. The amplitude is the distance from that axis line to the max or the min, so that's from here to here or here to here, and that distance was 1.5. The period is the length of one cycle, so I could go from a max to a max, a min to a min, or I could start right on the axis line. I think that's what I'll do here, is I'm going to find the distance from here to there. So there's one cycle. So that means we're starting at 0 degrees and going to, this would be 90 degrees. So that's going from 0 to 90 degrees. So therefore my period is 90 degrees. Now we're looking for the number of cycles that are visible. So I'm just going to highlight. So we've got 1 cycle, 2, 3, 4, 5, 6, 7, and almost 8. We have this little piece here, so that would be 8 cycles. The phase shift is the horizontal translation . The phase shift is the horizontal translation for a when you take this graph and compare it to a normal sine or cosine function. This graph could be a sine or a cosine because they're basically the same graph. One is just a transformation of 90 degrees, the other. So if you were to go back to these graphs, they're basically the same graphs, except that they're transformations of 90 degrees of each other. So for example, if you take the sine function and you translate it 90 degrees to the left, you're just going to end up with the cosine function. Or if you take the cosine function and shift it 90 degrees to the right, you're just going to end up with the sine function. So this could be a sine and a cos, and I could actually start wherever I want. So for example, here's a sine function here. So the phase shift would be the distance of this starting point to where it normally starts, which is on the y-axis. I'm going to determine the phase shift for the simplest sine or cosine function. So for example, where I started my first tracing of the period, that right there is 1 cycle, and it's starting on the axis line at the base of a valley, which is a reflected sine function because it does a full valley, full hill. So that's a reflected sine function. So there's no phase shift if I was to choose that to model as my equation. If I was to model with a cosine can start at its max or its min. So it starts at its min if it's a reflected cosine function. So I could start here and say the phase shift is from here to here, which is half of 90, and that would be 45 degrees. So I could say that's a phase shift of 45 to the right. If I didn't pick a reflected cosine function, I could choose here, and that would be a phase shift of 45 degrees to the left. The phase shift really depends on what part what section of this I'm going to model as a sine or a cosine function. So let's say I was going to model it from here. That is a normal cosine function, and it should start at the maximum value on the y-axis, but it's shifted over slightly. Let's just see what that value is. So if this is 90, this would be 45, and maybe half of 45 is 22.5. So we could say that's a shift of 22.5 degrees to the left. I could also choose it to be a reflected cosine function. So that would be starting here, and that would give me a phase shift of 22.5 degrees to the right. However, the simplest one here would be to choose something that has no phase shift, and that would be this reflected sine function. Instead of going up and coming down, it does a full valley first and then a full hill, and it's starting right on the y-axis on the axis line, which a normal sine function does. So I could say the simplest equation here would be a function that has no phase shift. But there is some ambiguity here. There's infinitely many answers for the phase shift. Our max value is at 0.5. Our min value is at negative 2.5. The domain for these functions is XER because it just goes on forever to the left and the right. And the range is always in between those two max and min values. So we're going from negative 2.5 to 0.5. Transformations of sinusoidal functions work the same as the other parent functions. We have those parameters a, k, d, and c, but these all have direct effects on these function properties like the period, the amplitude, and so on. So remember that this is a vertical stretch or compression. Well, this has a direct effect on the amplitude. So you could think A stands for amplitude. Whatever value is there, that is the amplitude. The K value is that horizontal stretch or compression, and so that's going to have an effect on the period. So imagine we're stretching the period of a normal sine function. The period of a normal sine function is 360. So if I was stretching it, the K value in here would be a fraction, and remember when I flip it, that becomes my stretch factor. And so if I am stretching a period of 360 by 2, I've now doubled the period. So now the period is 720. That's the same thing as taking 360 and dividing it by my K value. 360 divided by 1/2 is the same thing as 360 times multiplying by the reciprocal. So that's doubling it. You don't necessarily need a formula. I always teach my students to think of it in terms of the transformations. So again, if let's say I had a 3 in here, that represents a compression factor of 1/3. So if my normal period is 360 and I want to compress it by 1/3, I'm taking 360 and dividing it by 3, which is 120. So my new period is 120. So I think it's much better to think about these parameters in terms of transformations rather than formulas. The horizontal transformation here is what we already discussed, that phase shift. And then the vertical shift moves that axis line. So the C value is your axis line. I also made a note here that, for graphing purposes, it's good to note that the maximum value always comes from taking your C, which is your axis line. So if you have your axis line and you use your amplitude, you're going up the amplitude from C to get your max value. So your max value is C plus your amplitude. And then you're subtracting your amplitude from your C value to get your min value. So this is a good tool to use when you have to graph or if you're asked to determine the max or min from an equation. We're going to determine the following properties for this function. So we have our parameters A, K, D, and C. We're going to use those parameters to connect to these properties. So A is the amplitude. The amplitude here is 5. The negative pertains to a reflection, so it's irrelevant in terms of the size of the amplitude. So this is just 5. The equation of the axis, this has been vertically shifted up 3 units. So our normal axis line at y equals 0 is now at y equals 3. The period has to do with that horizontal stretch or compression. That tells us that our compression factor is 1/6. So we're taking our normal period of 360 and we're compressing it by 6, which is to divide it by 6. And that gives us 60 degrees. Our max value, if we want to give ourselves a little visual here, we said our axis line is at 3. So there's 3, and our amplitude is 5. So if I'm going up 5, my max value is 8. And then if I'm going down 5, 3 minus 5 is -2. My min value would be -2. The phase shift is given here. This is a positive D value of 85 degrees. So we're going 85 degrees to the right. Our domain for these is always XER because it grows infinitely left and right. And our range is between our minimum value. So Y is between -2 and 8. Graphing transformations of these functions uses the mapping rule again. So number 1, make sure your K value is factored out, then write the mapping rule. I always recommend that you figure out what the period is. So use your K value, determine that period, and divide it into 4. This is how you're going to label your x-axis. It's going to make the sketching much easier. I also suggest to find your max and min values just so you know when you're graphing, if you have to make the scale yourself, you know the highest value you're graphing and the lowest value you're graphing. Always draw the axis line first, so that's your C value. Then you're going to create a table of values using at least 3 points from the parent function. So remember, the parent function is either sine or cosine, and that's a full rotation. So starting at 0 degrees, 90, 180, 270, and 360. So we have coordinates for all 5 of these points. You can do transformations to all 5. However, I like to do just half of the pattern because then I can just use the symmetry of the graph to keep going, to graph the complete cycle. So let's graph this one. First thing I'm going to do is make sure the K value is factored out. So I'm going to take out that 2, and that gives me x minus 30. Now I can see the proper phase shift. So I'm going to go through and figure out what the period is. That K value is a horizontal compression by 1/2. So I know my period is 360 divided by 2, which is 180 degrees. So when I go to do my scale, I'm going to take 180 and divide it into 4 pieces. So that's 45. So 45, 90, 135, 180. Okay, my max value is starting from my axis line, which is here at 1. So I know my axis line is going to be here. So my hills and valleys should be going around that axis line. The amplitude is 3. So I know my max value is going to be 1 plus 3, which is 4. And my minimum value is going down 3 units from 1, which is -2. So that's good on my scale here. I have 4 and -2. That's my highest and my lowest. Now I'm going to make the mapping rule. So I'm going to think about all my horizontal transformations. We're compressing by 1/2, and then this means we're going to the right 30 degrees. So I'm adding 30. Out here, we're reflecting it and stretching it by 3, and then we are going up 1 unit. So I'm going to write the first 3 points of the normal sine function. So remember, the sine function is measuring the y values as we rotate around the unit circle. So this is 1, 0, and -1, 0. So the sine of 0 degrees is the y value, which is 0. The sine of 90 is 1, and the sine of 180 is 0. I'll put my horizontal transformation here, my vertical here, and in here we'll put our new points. So plugging in 0 here gives me 0 plus 30, which is 30, and 0 in here gives me 1. So there's my first coordinate. Then I'm plugging in 90 times a half, which is 45, and 45 plus 30 is 75. And then negative 3 times 1 is negative 3, plus 1 is negative 2. Then 180 times a half is 90, plus 30 is 120, and 0 plus 1 is 1.